Okay, so this one, I'll just kind of talk about and start a few of them and let you finish. So this one talks about vectors -3, 2, and -7, -4. And so are those coordinates, those places in the plane? No, right. Components of vectors represented what again? Remember? Yeah, what are the components represent? Variation, amount of change or variation, right? So in the horizontal and vertical directions. So I could put this vector anywhere just as long as it's heading to 3 to the left and 2 down. So for instance over here, 3 so I can start there and go 3 to the left, 1, 2, 3, 2 down. There's my other way, 2 up. Just kidding. All right, and so then like this. So that's would be one representation of u. And I could put it up here. I could put it anywhere. But I can also put its tail at the origin. So -3, 2. And so that's called standard position. Standard position is when you take the vector and you move it so its tail is at the origin, and then something special happens. What happens that's special when you put its tail at the origin? So we got the vector -3. What do you notice? What's that? So what is that called? The tip. The tip has coordinates now. The same as the components. You see that? Because the variation or the change from 0 will put you, that's what coordinates mean, right? Coordinates mean how far you are with your variation from 0. So going over 3 and up 2 from your starting point, if the starting point 0, 0 is going to put you at that point, -3, 2. Does that make sense? Okay. And then what's my other vector? -7, -4. So something like this. I'm going to also put that in standard position, vector v. And now it's saying that, so you see that you get a unique parallelogram from those two vectors. And I put them tail to tail. There's a unique parallelogram that you get. And that parallelogram has diagonals. So notice this side of the parallelogram. How could we also talk about that side of the parallelogram? This dotted line here. He said it's also vector v. Agree with that? Yeah, it's also vector v. All right, so also vector v. This one is also happens to also be vector v. And then similarly, this is vector u. So looking at this longer diagonal here, how does that longer diagonal relate? This is the question when you ask. Don't answer it, but this, in order to solve this problem, you ask. Looking at that longer diagonal, I've got u here like this, and then v here like this. Sound effects included, right? U and then v. How does that longer diagonal relate to the vectors u and v? So if you remember what we talked about from the first class, you should see a very important relationship there. That longer diagonal has a very basic relationship between u and v. Okay? Yep. Think about it. Think about that. And then the shorter diagonal also has a very unique special relationship between vectors u and v here posted or plotted tail to tail. Yeah. And so then it's asking for the what? The lengths. If you have these vectors, getting the length of those vectors is easy, right? So first get vectors that represent those diagonals, and then the lengths are easy. Okay, so that's a little help on that one. Next question, number 5. Or no, actually, yeah, let's talk about number 5. Okay, so we have a ship. And the ship is heading north at 1 mile per hour. Best ship I've drawn all day. 1 mile, so 1 mile per hour north. And then on the ship, the child is walking 4 miles per hour east. Let's find the speed and direction of the child relative to the surface of the water. So what has speed and direction of a moving object? What would that be? Speed. What kind of vector? That's what we call the velocity vector, right? So the velocity vector written in its components would have a horizontal component to the velocity and a vertical component to the velocity. What's the horizontal component of the child's velocity? That's how it's walking, to the right. And what's the vertical component? So the combined effect of the boat moving 1 mile per hour north and the child walking 4 miles per hour to the east is the child's velocity vector relative to the water, right? It's giving you the horizontal and vertical components, so you can write them down. Okay, and so then speed and angle from the north, right? So the child's, we draw these in proportion here like this. So it's going to be asking for this angle. So speed will be what? It'll be the magnitude of that velocity vector, and then they want this angle. So I think you can finish that one. Questions on that setup? One more to talk about. Let's talk about go back and look at number 5. All right, so a wind is coming from the west at 51 miles per hour. So what kind of vector could we use to represent that? It's coming from the west at 51 miles per hour. Displacement vector? Force vector? So that's speed, right? If you got speed and you have its direction, then we got what kind of vector? Velocity. Coming from the west, that is a west wind. Winds that blow from the west to the east are west winds. Okay? And so that would be, we could put that in standard position like that if we wanted. And then we know that that vector, the magnitude of that vector is 51. And then they want to fly north, right? So they want to fly north. Resultants, meaning the result of everything that's going on, we want to be this vector north. And so which way should they face or travel in what direction? So the resultant would be this way. So they said they're going to head northwest, right? They're going to head northwest, something like this, at some speed. They're going to head northwest at some speed, so that the combined effect of the wind blowing like this and they're traveling in this direction is resultant like this. Now notice, these are not displacement vectors. So these are not like points on the map. These vectors are all about what's happening right at that point, right at the origin in terms of speeds, of velocities. So it's kind of like we're using displacement vectors, but we're not using them as displacements. We're drawing them as displacement vectors on the plane, but what we're thinking about is that how these are representing a situation that's happening right at the point of travel in terms of direction and speed. Make sense? Okay, so we want the combined effect of the wind and their travel to result in that. So what operation of vectors are we talking about? If we want the desired effect of these two together to give that. So we're going to combine these two. What operation is that? Addition, right? So the addition of the vector of the wind and how they're traveling should result in straight north. Okay, so addition means what? Tip to tail, right? So I'm going to add the wind plus their trajectory, right? So their speed and direction in the northwest direction. And so let's write these vectors as components. What will be the components of that vector right there? This velocity vector, wind vector, in component form. All of it is to the right, right? So it'd be positive 51, 0. Okay, so this now is what? The northwest. So this is a 45-degree angle. So we don't know how fast they're going to go, but as components, you do know something. If this is a 45-degree angle, what do you know about the components? Same magnitude, but what about signs? What about the horizontal component? Negative something. And then, therefore, if this is a 45-degree angle, this component would have to be positive, that same something, right? And the result we need to be, what about the components of that vector? The result we need to be is, what about the x component? 0, because we need to be straight north. Does it make sense? And then this is some new value to the north. So I think that's a lot of help on that one. Take it from there. Did everything make sense? Ask if I lost you. Okay, and then what we're about to do is going to be more help on other problems on this first web work. Yes? Okay. Please.
How would you find what speed they need to be traveling north if you don't know how far they're trying to get?
So I think it's understand. So how we've modeled each of these three vectors, and then knowing how those three vectors are related will do it for you. Right? So the combined effect of these two gives you that. So think about what operation is that, and then we've got those three vectors and. Yeah, I guess that's true. Yeah, but I mean, even if I say it's an unknown, you very quickly would come up with the same result. Yeah. Okay. Other questions? All right. So let's do what's next here. Oh, another slide. Let's talk more about vectors here. Copy. All right. So a unit vector, we talked about special unit vectors last time, but just a unit vector is any vector, but it has to have a magnitude of 1. Super important, right? A unit vector, it's a unit long. A unit is like 1, right? So a unit vector has a magnitude of 1. And we talked last time about the standard basis unit vectors. For R2, the standard basis are I and J. So you're going to write those because you can't write in bold. You will write those as I with an arrow, J with an arrow. It's the same thing. Hard to write in bold, but you'll see it on web work and in textbooks. You'll see vectors represented in bold. It means the exact same thing as cursive with an arrow on the top. Okay, and so every vector can be written as a linear combination of I and J in R2. And then in R3, we've got 3 dimensions. So there's 3 standard basis vectors, I, J, and K. So just as quick practice here, can you write all 5 of those in component form? So what would in component form, what would all 5 of those be? Go. So everyone write those down. Yes, and you can talk. You can talk if you want. So for R2, just alphabetical order, like X, Y, Z, I, J, K. That's how you can remember. Okay, so in the, yes, the blonde hair, yeah. Tell me your name. Emily, how'd you do? So what's I in R2?
So I and R2 is I R1 and 1.
Just the number 1? So what are the components? Like, so you got, for R2, you have an X component and a Y component.
Oh, 1 and 0.
1, 0, okay, good. And then?
0 and 1.
0, 1. Okay, so now thinking about, so, well, how many components will our vectors have in R3? 3, right? And so then the I will be 1, 0, 0, right? And then J will be 0, 1, 0, 0, 0, 1. So those are special unit vectors. But any vector that has magnitude 1 can be any direction is a unit vector. These are the special unit vector called the standard basis unit vectors. Okay. All right, so remember we talked about multiplying vectors by a scalar. What happens when you multiply a vector by a scalar? So let's, for instance, how would 3u compare to u? How does the vector 3u, what does it represent relative to u? Nick?
It would represent the magnitude is 3 times u.
Okay, and what else? What's that? Same direction, right? Same direction as u. 3u would be same direction as u, but it'd be scaled up by 3, so its magnitude would be 3 times as much. Okay? What about negative 0.5v? What about negative? Yes?
It would be
Scaled down by half.
And it would also be in the opposite direction.
Flipped in the opposite direction. So now we're shrinking the vector to be half of its size, but then we're flipping it and pointing the exact opposite direction as what v was before. Okay? So scalar multiplication, so in general, scalar multiplication always gives a vector that's parallel, either in the same direction or exactly the opposite direction, and then it scales it by whatever that factor k is that you're multiplying by. Okay, so how can we find a unit vector in the direction of 3i minus 5j? So in component form, how could we write that vector? If I take 3, right? If I take 3 unit vectors in the direction this way, then I've got an x component of 3. And if I take negative 5 of the j vector, which is 0, 1, I'm going to get, what, 5 down. So is this longer or shorter than a unit vector? Right? What is the magnitude of this vector? Square root of 34? So this vector has a magnitude of square root of 34. I want a unit vector in the same direction as this one. So therefore its magnitude needs to be 1, right? If I want a unit vector, magnitude is 1. So our vector, what? It's radical 34 times as long as the vector I want. Right, or multiply by, scale it by. How much would you scale it by? So you actually shrink it down to a unit vector. 1 over. So I shy away from, you rarely see vectors divided by something. So keep it to multiplication. Sorry, I got to remember that I can't use the bottom of the screen. So our vector is radical 34 times longer. Therefore, I've got to shrink it or scale it down by 1 over radical 34. And so now that's a unit vector in the same direction as the original vector. Unit vector, so it has magnitude 1. Make sense? Okay, so then the next step would be given a vector. I'm going to change it. You can't read that. So great frustration. There we go. You can read that. Is it big enough to read in the back? Is that type? Can you see it? But I'm going to change this to negative 2 minus 7. now I want to find a unit vector with magnitude 8. So my in the end, the magnitude of my vector is 8, and I want it in the opposite direction of negative 2i minus 7j. So rather than me tell you how to do it, I'd rather have you think about it and see if you can have a roadmap for a solution for this, based on what the one we just did. Okay, so think about it. If you're having trouble making progress, then you can get help from somebody. But you're either making progress or getting help.
So first, you wrote components,
Which is
which is -2, -7,
beautiful. Okay,
and then solve for the magnitude.
magnitude is
Started at 53.
magnitude of this vector. You can write it this way. 53. Okay, good.
And then we made it into a unit vector.
Okay.
So we multiplied the components by 1 over square root of 53.
So this is the key. If you can come up with to do a unit vector first, then those are easy to scale, right? They're magnitude 1, so you can scale into anything you want. So here's the unit vector. Okay. And then?
And then to make it the magnitude of 8 in the opposite direction.
Yeah.
Multiply that by -8.
So take a negative 8 times that. Well done. And so you'll get what? Positive 16 over rad 53, positive 56 over rad 53. So yeah, so the key is this kind of two-step process. If I want something with magnitude 8, well, the easiest way to get a vector with magnitude 8 is to multiply a unit vector by 8. So get a unit vector first, and then multiply by 8.
And then I can do like times by
Questions on that? Okay, what's next?
Yeah, I did.
Force example. So let's do another real-world example here. Okay, so we got force vectors A and B applied at the origin as shown. Find the component representation of each vector, and then the vector that gives the resultant force at the point. Resultant means combined effect, overall effect of applying these two forces. Kind of what resulting one force is the combined effect of applying the force A and B together. Again, we're drawing displacement vectors to represent a situation that's happening where? Just at the origin, right? In this situation, there's nothing about this point, right? There's nothing about this point in the plane or in this situation, the location of this point. The location of this point is not relevant. This situation is modeling something that's happening only at the origin, the force applied at the origin. So we're kind of melding displacement visualization with the force situation. Make sense? Okay, so these vectors now are given in what's called polar form. Polar form is kind of back to our original definition of a vector, that vectors have magnitude and direction. And so that's how they're given here. Polar form is the polar form of A is the magnitude is 4 kilonewtons, and the direction is 40 degrees. That's like a trig angle, right? So then so what we need first is component forms of both A and B. So component form would be, what would be the x component of vector A and the y component of vector A, given that it's a 4 kilonewton force at 40 degrees. So the x component of A is like this vector here. And the y component of A is like this vector here. So I have to draw on our previous math knowledge. How am I going to get the x component, knowing that the magnitude is 4 at 40 degrees? What would the x component be? Nick knows. Samuel, what do you think? You know how I get this component right here? given 4 in this direction at 40 degrees north of east. Cole, what do you think? 4 cosine 40. Is that what that is? Absolutely. 4 cosine 40. 4 sine 40. It's going to be the y component. All right. Now, on B, we got to be careful here. Cosine and sine operate on what kind of angles? Angles swept counterclockwise from the positive x-axis. So, a couple different ways to do this. So the B vector is, what is the x component of the B vector? X component. Jeff?
I got 2 cosine 170.
2 cosine 170. What do you think? And that's going to give us what kind of number? X component to the left, right? So it should give us, and that's what cosine does in the second quadrant. It gives us a negative value because the x coordinates are negative. What would be another way to do that then? If you were just want to use the 10. That's the same as what? You'd have to throw a negative. If you do cosine 10, you got to throw a negative on there, right? Because cosine 10 is positive. So, all right. Then what about the y component? 2 sine. In here, you could use 170 or 10, because sine is positive both in the first and second quadrant. So we'll just be consistent. We'll use 170, but 2 sine 10 would be fine, knowing that sine of 10 is the same as sine of 10, sine of 170. Okay, so how am I going to write the overall force vector then? So the overall force that's happening at the origin due to the combined effect of A and B would be, what kind of thing, operation, calculation will I do? What's that? She's offering up addition. Addition? Yeah, we're just adding together the combined effect of A and B to get the total. Okay, and how do we add vectors? Add the apples. The beauty of component form is apples to apples, oranges to oranges. We can add x components and y components. So anyone got decimal approximations for these?
For A, it would be 4 cosine 40 degrees would be 3.064.
Let's do this. So I'm just going to add, say it again.
Oh, sorry, I forgot to add them on there. So it would be
Anyone got it? Just shout it out as soon as you get it.
1.09.
What is it?
1.09.
1.09 kilonewtons. And 3 point something, if I remember. And is that, what happens on that x component, is that like truly an additive effect or a canceling effect? You got a canceling effect, right? If you're pulling with so much force this way and then so much force this way, they're going to kind of cancel out. But since the A has a larger x component, we're going to end up with a force to the right, a positive x component. What about y? What about those? Canceling effect? Adding, right? Combined effect. You're pulling up in both situations. So you're going to just add them together, add 2 positive values together, and you get 3 point something, okay? So that's component form of the resulting vector. And if I'm adding vectors, if I want to show that visually, tip to tail, right? So I can throw B here, like this. And then the resulting force vector would be like this. Does this, what I'm drawing, match up with the values of our components for the resultant force? Yeah, 1 point something and 3 point something. That looks like about what this vector is. The combined effect of those 2 force vectors is that force. How would I get the magnitude of the force? The magnitude of that vector, right? Square root of the sum of the squares. Yep. Take the magnitude of that vector. How about the direction? So I'm doing polar form now. Polar form is magnitude and direction. How would I get the direction of that vector? If I've got 1.09 and 3 something.
It would be a 2.9. Two.
Well, this is the y component is 2.92.
Yeah, in
Sorry.
radians it's 3.6.
Wait, this is a. It's not an angle. Why are you saying radians? It's not an angle. Is the y component 2.92?
Yeah.
Okay,
One
thank
is
you.
The answer with 3 is it was with using radians.
But that has nothing to do with radians. Radians is an angle measure. So yeah. Sorry, 2.9 something. 2.92. Okay, and so magnitude of the force would be. The magnitude of that vector, and then the angle would be, how could we get the angle from those two components? Inverse what? Inverse tangent, right? And you could even after you found the magnitude, you could use any inverse function you wanted, because you'd have that length of that hypotenuse. So you could use inverse sine, inverse cosine, but going back to the original components, we could do arctangent of opposite over adjacent. And then, what? So that should be something between 40 and 90, right? And if you do the math, you get, I remember that one, 69.4 degrees. Okay. Questions on this example? Yes, please.
So that was a lot here, so I'm just trying to understand, deconstruct this a little bit.
Yeah.
So the angle degree from the new addition vectors that we kind of put together,
Yeah.
that's the resultant force.
The resultant force was when we added the two A and B together.
What was the component of that?
This is the components of the resultant force. Now from the component form, now we're changing that to polar form. That means find the magnitude of that vector. So sum of the squares and the angle. And so the angle is just a right triangle problem. They're both right triangle problems, right? So the magnitude of the resultant force is just taking the components and finding the hypotenuse. And then the direction is just this angle from this right triangle. So this is tangent of that angle is opposite over adjacent, so we do arctangent to get the angle. Does it help? Cool. Other questions? Okay, so let's go back to talking about R3, right? R3. So hopefully that, in terms of just the pure vector stuff on the web work, you think you're set to go now. So here we go. So we were looking at this point, 3, 4, 2. So this, in my view, on my screen, this is almost horizontal. Is this almost horizontal to you on the screen up there? Like just a little bit tilted down?
Yeah.
Okay, good. To me, it looks like it's. Okay. All right. So 3, 4, 2. Oh, so let's before we do all this. So we got 3 axes here. We got the x-axis, y-axis, and z-axis. So which one is the x-axis? Do you remember from last time? Coming straight out. So this down and to the left is just a way to trick your eyes. I need a yardstick. Here we go. But what you're imagining, that down and to the left is fastest axis in the west. Okay, like this. Okay. This axis right here is supposed to be tricking your eyes. So this, okay? Yes? Does it make sense? So this is truly what's going on. And then our y-axis is which one? To the right, and z is up. So the 3 axes form 3 planes, okay? So what is the yz plane? How would you describe the yz plane? The YZ plane, yes. And where is it? Where is it relative to the screen? It is the screen. It's the screen. The YZ plane is the screen, or your paper, whenever you draw this. Okay? So the YZ plane is the screen. Okay, what is the XY plane? The XY plane. Like the floor, right? So it's this horizontal plane. The XY plane is horizontal. It's like this. And then the last one is the XZ plane. XZ plane. Is that vertical or horizontal? Vertical. How does it compare to the screen? Perpendicular to the screen. Or parallel to that wall over there, or parallel to the windows. Right? That's the XZ plane. All right, so then those three planes, they break up space into 8 octants. So remember remember that our XY plane is the horizontal plane, right? This is our XY plane. So where is the first quadrant in the XY plane? First quadrant is here. And then second quadrant would be here. Third and fourth. So it's a little different. I gave it a twist, right? We gave it a 90-degree turn. So first, do you see that this is 1, 2, 3, 4? Do you see that? This is 1. Lower right is 1. This is 2. Back in the back left is 3. Forward left is 4. Do you see that? Okay. So what about octants? The octants are the same way. So you got 8 octants that are broken up by the 3 planes, and you kind of count them the same way. The first 4 octants are just like the first 4 quadrants, but above the XY plane, and then the last 4 are below. But really, the most important one is most of the time we talk about the first octant. So where's the first octant? X, Y, and Z are all positive. So this point is in the first octant. The point +3, +4, +2. That's showing in the first octant. Second octant is back behind that, back up here. Third octant, back up here. Fourth octant, in front over here on the left. And then 5, 6, 7, 8, same thing underneath the XY plane. 5, 6, 7, 8, down below. Okay, so my point here, 3, 4, 2. How far is that from the XZ plane? That's my point, 3, 4, 2. What's its distance from the XZ plane? 3? So it's be going along this one, right? Wouldn't this be its distance to the XZ plane? And which coordinate is that? That's the y coordinate, right? So the distance to the XZ plane would be 4. All right? What about the distance to the y-axis? How far is this point to the y-axis? So what's the key point I'm looking at to find the distance from here to where? Yeah. To the y-axis? Y-axis. So tell me the coordinates of the key point that I'm looking at to find the distance from this to the y-axis. What would the coordinates of that point be? Be this point, right? This is the shortest distance to the y-axis. The coordinates of that point are? 0, 4, 0. And this is 3, 4, 2. So the distance would be along here, whatever that distance is. So we could start, how could we do this? We could make a vector, right? What 3-dimensional vector, R3 vector, is from 0, 4, 0 to 3, 4, 2. So let's call that vector, not D. Call it vector A. What vector goes from 0, 4, 0 to 3, 4, 2? X component is? 3, then 0, and 2. Final minus initial, right? So 3 minus 0, 4 minus 4, 2 minus 0. Okay, so I want you to find the coordinates of Q. This is point Q. Find the coordinates of that point, Q. Find the coordinates of the midpoint of this down here. Call that P. That's the midpoint of that thing. Find the coordinates of that. And then I want you to write vector QP, which would be this vector here. That's vector QP. So coordinates of Q, coordinates of P, and then vector QP.
Hey, Ash.
Yeah.
So,
Hey, Juliana.
so is the thing I said earlier, is that distance to the YZ point?
Yes, right. So the x coordinate, was it 3? So it's 3 away from the YZ plane,
Okay.
but it's whatever that is away from that y axis. Make sense?
Yes.
So,
Do you guys hear that question? When I ask how far is this from the y-axis, that's to this point. The distance to the yz plane would be, this would be your key point here. You would want perpendicular, so that's just 3. Distance to the yz plane is 3, but the distance to the y-axis would be this diagonal down to the axis. Does that make sense? Okay, so you got this task. Coordinates of q, coordinates of p, and write the vector qp. Go. Coordinates of point Q are 302. Coordinates of point P 1.540, making the vector QP negative 1.5. It goes back into the x component is negative. It's going back into the board. It's still in front of, but it's heading towards, heading backwards. Negative 1.5, 4, negative 2. That's a 2, not a 1, sorry. Okay, very good. Okay, so, and what's the distance from Q to P? How could I find the distance from Q to P? Now that I've got this vector, right? It makes it easy. Magnitude of the vector. So the magnitude of QP, 1 bar or 2, doesn't matter. Take your pick. 1 bar or 2 means the same thing. Square root of 5 squared plus 16 plus 4, whatever that is. Okay, one more thing we need to go over a little bit because I want you to have it for the homework. Any questions on QP, the magnitude of QP, which ends up being the distance? So the magnitude of the vector QP is the same as the distance from point Q to point P. Okay, so now this point is what? What's this point? I want to call this C. What point is C right there? 3, 4, 0. Right? That point's 3, 4, 0. I want to find all points a distance of 2 away from that. I want to find all points a distance of 2 away from that. So how can I represent all points that are distance 2 away from that? So first of all, x, y, z, right? So this is a coordinate of a point that's 2 away from that. So I can make a vector, right? I can make a vector from C to that point. What would it be? What would that vector be? Starting at C to any point x, y, z that's 2 away. So what would that vector be? X minus 3, right? Final minus initial. Y minus 4, z. Is it okay? And what did I say? I want every point such that the distance is 2. So what could I set up here to make sure that those vectors are correct? The magnitude of this vector is 2, right? Almost done. Does that make sense? Does that make sense? So I just took the magnitude of that vector, and I'm setting it equal to 2, and that forces the ordered triples x, y, and z to be 2 away from the point 3, 4, 0. Has to be. Okay, now I want to square both sides. What are all those points that are 2 away from the point C?
just here.
right? Isn't C the center of the sphere of all those points? So if I type in this, if I type in that equation, there it is. I just typed it in. X minus 3 squared is y minus 4 squared plus z squared equals 2 squared. What will I see? What's your favorite color? I heard red. So I get all the points that are 2 away from that corner point on the box. And all those points are a sphere. So that when I put a box around there is the equation of the sphere, where the center is. Yeah, so x minus a, y squared, y minus b squared, z minus c squared equals 2 squared. So the center is the a, b, c is the center. The radius is the 2. So you're going to square the radius, x minus, and then x, y, z stays x, y, z because it represents every point on that sphere. Okay, so